Thank you very much for the invitation. I'm happy to be here, although a bit outsider. My main field is combinatorics, discrete mathematics, but there very often I use at least some beautiful results from logic and from other fields of mathematics, of course. And the other thing is that I hope that I can ask questions which you can answer, or at least to point to a possible solution. I have a really ambitious plan today, so many things to talk about, but we will see how it goes. So my plan is to talk about regularity lemmas. And extensions. So just to mention one, the blowup lemma, and then hypergraph regularity, which itself would be a full lecture just to go through all the introductions and everything and notations and juggling with epsilons and deltas. But I will offer you a very short version of it, a very powerful statement, easy to understand, and hopefully very easy to, easy to use and turns out to be very useful. That's my hope. And maybe an application here, an application in group theory. Group theory somehow goes through many of those questions here. Well, we will see what to do there. Second large, type of questions I want to talk about. Some examples from Erdős type problems. Well, there are many, but in discrete geometry. And this title, as it is, even has its, what is this MSc code? You know those, like the classification. So there is one with this title. I was surprised to learn that. Anyways, now I know. And here, well, I'm interested about questions like this, that here is a Cartesian product just in 3D. It's like a Cartesian product of three sets, A, B, C. And it happens that there is a relatively low degree variety, algebraic variety, which, drawing is harder here than I thought, which has a large intersection here. So if we have the model that A equals B equals C equals, say, n, a number, it's finite, and what can we say if there is an algebraic, if there is a polynomial that its zero set has many points from this Cartesian product, close to n squared, or n to the 2 minus c, well, or even n to the 1 plus c. Is there anything one can say here? And hopefully yes. Well, there are much more general theorems dealing with problems like that. Udi has a series of theorems which could apply here, but let's just see the simple approach here. And then finally, which is somewhat continuation of this, but a special and very important subset of problems, is incidence problems. The simplest family of problems here is concerned about points and lines just in the plane, in the real plane or complex, it doesn't really matter, or even over finite fields. What can we say if the number of incidences between a point set and arrangement of lines is large? One would expect that there is a structure behind it, but it seems to be hard to achieve. So those are the three things I plan to talk about. And let's see if I learn my lesson. No, I did not. Let's see the other end. Maybe. Yes. But before I begin, it goes pretty high. Before I talk about regularity, I can't resist to talk about something which I'm not going to talk about really, is the connections between combinatorial number theory and of course logic and algebraic geometry. So there is a beautiful problem. I heard it from Erdős. Many problems which I'm going to talk about, I was lucky enough to hear it from Erdős himself. But this is, there are two authors of this problem. This is the Erdős-Ulam. I stated conjecture. And this is about points on the plane. The question, I write it as a question, that is there an everywhere dense subset of the plane such that, so those are points, subset of points in the plane, so that such that all pairwise distances are rational. This was one of my favorite problems. The first question is that just try to find points where all the pairwise distances are integers. Then for rationals, then you can check that you can easily find such a set on a circle or, of course, along the line. There were tries to find points along curves or something. There was a conjecture of Erdős that if there is such an infinite set, then the limit sets, the limit points are very special. And this is still widely open. With my student, we proved that at least if you have an algebraic curve, then the number of points there on this curve, that the pairwise distances are rational, that's finite for every curve. And here is the surprise. Well, it wasn't really a big surprise because we already used Folting's theorem there, but Terry Tao, and independently Jozsef proved, extending this curve observation, that R squared. It's a plane, it's a planar point set. That if the so-called Bombieri-Lang conjecture holds, then that would imply a strong form of the Bombieri-Lang conjecture holds, then that would imply that there is no such point set. And well, Bombieri-Lang is a much stronger form of Folting's theorem. And well, that happened like 2 years ago, or no, maybe more, 4 years ago. I was in Italy. So, but here is this is not, well, it can be already connections to logic, but here is the paper I just find, that definability of Frobenius orbits and results on rational distances by Hector Paston. And he proved that actually, if ABC conjecture holds, then it's also true. I mean that there is no such set everywhere dense, that all the pairwise distances are rational. I don't know how it goes, but there are some famous central theorems or conjectures which would imply this. Maybe there is another way to approach. I don't know. I definitely wanted to mention this beautiful problem, and I used several minutes already on something which I was not planning to talk about. But let's see regularity. Maybe I will just sketch some of the parts. It's kind of flexible. If time permits, then I really will talk about all of those. But regularity lemmas. So I won't even state it now, but there are some exciting new developments here, connections of regularity lemmas, in particular for stable graphs, which I will define in a minute, and recent results of Marianis and Schellach and with Pillai, that's a follow-up paper on graphs. So graphs in our case, it's just vertex sets and there is an edge. So it's just a symmetric, simple graph for us. And regularity lemmas usually applicable for huge graphs, very large and dense graphs, because it will say something about the possible partitioning of the vertex sets into not too many parts, that in between those classes, the graph is epsilon regular. Epsilon regular means that no matter how I choose an epsilon fraction here and there, the number of edges, the edge density, will be pretty much the same with a very small error than the edge density between the big parts. So it's slightly, well, it's a very weak version of quasi-randomness. It's not even really there, but you would expect that if it was a random graph, then the number of edges between two large parts, the density is pretty much the same in every part, like in the big one. So this goes into structural graph theory, and it has very powerful applications, but also its origin comes from number theory. Samaridy applied a tool similar to this to prove his theorem that if you have a dense subset of integers, then there will be arbitrary long arithmetic progressions. So the recent result is about stable graphs, where there is a very strong condition that suppose that our graph doesn't contain an induced half graph. The half graph is a bipartite graph. You can label the vertices. I just use the numbers up to k, say, and 1, 2, up to k. And now from here, or say from the top, you connect all the other vertices which have larger labels. So now 2 is connected to 2 and everything above, and you go further. So this is half graph. It's kind of self-complement, so you can see from the other side. If you forbid for any k such a graph, then the graph is called stable, and there are reasons for that. But anyways, then the result is that there is a very nice regularity lemma compared to the original one, in a sense that because of exactly those graphs, in original regularity, you need you have a tower type bound on the number of partitions which are needed. But if you forbid this graph, then it's just exponential, which is much better. On the other hand, it comes with a price. If you forbid anything, any bipartite graph as an induced graph, then between two large parts, the density is pretty much either 0 or 1. There is no other way to avoid it. If you have an epsilon regular graph with some, say, half density, then you can build anything, any bipartite graph there as an induced graph. That's just a technical thing, but it's a relatively routine step if you work with regularity. So, but this is, well, this seems like a big problem, but it still opens some possible applications, because this is not unusual. When you define your graph, say, you have intervals in the plane, and you just connect two if they intersect each other. So this is so you define your graph based on, well, in this case, it's a very simple semi-algebraic kind of relation. Then you have this 0-1 rule. You can check, because there are many forbidden substructures which you can't avoid. So still, there is hope that there will be applications of those results in various parts of combinatorics. There is one already, namely that if you forbid this graph, then the so-called Erdős-Hajnal conjecture holds for this graph, which I won't even talk about because that's graph theory, and let's just switch to generalizations of the regularity lemma, which I didn't even state correctly yet, but strangely enough, it will be easier to talk about it in a more general form. And that's what I'm trying to do. So first, just one possible extension of this result. I think that one can go a little further and one can prove the so-called blowup lemma, which is due to Komlós, Sárközi, and Szemerédi. And it's a very interesting lemma, and it tells you something about the possible applications of regularity and regularity lemmas, but it goes beyond. It's much stronger. It says the following, that, well, there are parameters which we will see, or will be obvious what are those parameters. But let's begin with any graph. It's a finite graph we begin with. There is G. And, well, it's an arbitrary graph, as I said. This is quite arbitrary, but let's stop here. And now, from here, we will produce two graphs, G prime and G2 prime. G prime, it's a blow-up lemma, and the blow-up comes from that every vertex now is substituted by a set of vertices, a huge set of vertices. So this was a constant, but now the number of vertices in each class is n, and n can grow or whatever. It's up to us. It's an independent parameter. One more. And wherever there was an edge, now you place a complete bipartite graph. So let's place a complete bipartite graph here, and, well, everywhere where we saw an edge. So this is a complete bipartite graph. G2 prime is a similar graph, I mean the same vertex set. So here we have the same vertex set, but instead of placing there a complete bipartite graph, we put there an epsilon regular graph, not only epsilon regular, and epsilon regular, you remember, that means that every, at least epsilon fraction, has the same density, or very similar density than the original one. But an additional condition that there's another parameter, delta, that every degree is at least delta. And you will see why it's necessary from the statement. So epsilon regular pairs with the extra condition that the minimum degree, if those sets have size n, the minimum degree is at least delta times n. Okay? And here's the statement, the blow-up lemma, that choose any graph H, but bounded degree, that's another parameter, where the maximum degree of H is smaller or equal than a parameter delta. And embed it. So suppose that this is a graph which you can embed to this graph, this blow-up graph, which is full with complete bipartite graphs. Yes? If you don't want to choose H ahead, then you just play with it, and you do, and you choose your next neighbors. This will follow the structure here, but the only condition is that you can't visit a vertex more than delta times. Okay? But then the statement is that if, so I write it maybe here, that if edge is embeddable in G prime, then so in G2 prime. So bounded degree vertices can't distinguish complete bipartite structure from regular structure. And this is harder to prove, but please note that this is a perfect, it might be a complete subgraph of this. So you can use all the vertices. There is no room for any error. So it's really a complete cover if you want. If you want, then the number of vertices of edge is exactly the total number of vertices here. So this is a strong statement. It says that actually regularity is very similar to complete bipartite. Now this still has applications, and it would be interesting to see if one can get a similar statement using for stable graphs. Now,
big delta is bounded?
so everything is constant. Here is a constant. Here is a constant, and the graph G itself was constant.
But n is much larger than delta? Which one chooses?
N grows, and well, in order to satisfy those conditions, yeah, so you write there should be an n larger than some n naught, which depends on the parameters. And there is an epsilon for epsilon regularity, and the size of G.
And you replace each graph by each vertex by n points.
Each vertex by m points, yes. So this, I think, can be done. There are other, well, maybe one, no, but okay, I don't have to talk about stable graphs too much because Julia will say much more about stable graphs later on. So let's see. I promise that I will give you a simple statement which has almost all the powers you ever need from hypergraph regularity. It's a very powerful statement. I mean, it's a powerful tool. Hypergraph regularity, or rather its corollaries, those came from an old conjecture, which is still open, unfortunately. So even this tool was not enough to prove it. So the conjecture is, it's a beautiful conjecture. It's Brown, Erdős, Zsozs conjecture. I will write it as K plus 3 K conjecture for 3 uniform hypergraphs. In this case, hypergraphs are nothing else. You have a base set on n elements, and you consider some of the triples. So some of the 3 element subsets. Those are the edges. So this is a 3 uniform hypergraph, what we have here, if all the edges have 3 vertices. And, well, you can have n choose 3 of the edges, but here is a conjecture. It says that if the number of edges is quadratic, something like c times n squared, then let's see a special case first. 6, 3, that would be the first meaningful statement. Then you will find 6 vertices which carry at least 3 edges. So there is this local condition that locally you will find something based on a general density statement. This is actually, this is a theorem. This is Jozsef. So let's write it for this case, Jozsef. It says that if no 6 vertices carry 3 edges at least, or more, then the number of edges, which is just the selected triples, is little n squared. So it's sparse, very sparse. So you can think that n squared is a kind of simple bound here, because if you had many triples sharing 2 vertices, then immediately you have 6, 3. So if you had like 2 and 1 edge and another one, those have 1 more, and another one, you see, if you had a pair of points which are points of 3 edges, then it's done, because here you have only 5 vertices and 3 edges. So actually, in this case, n squared is a kind of trivial bound. And you can suppose that your system is linear. They say it's linear if the intersection of any 2 edges is just 1 or 0. But let's just stay here. So to prove this, they used regularity lemma. And 7-4 open. Nobody knows. Yes?
So the graph that you're looking at is very large, and when you say all of n squared, you mean when you pick n points from the graph?
The number of edges is ordo n squared, so the number of triples, the maximum number of triples you can choose without a 6-3 configuration is little n squared. So it's less than quadratic. And it's little also exponent. You can't really hope for 2 minus c. That comes from Behrens construction, but let's not. Okay, so 7-4 is open. That would mean that, so what is the question here? You have a subset of 3-element sets from your base set, and no 7 points carry 4 edges. So this is open. I proved it for a very special case when you have a group in the following sense. So for finite groups, I write here just that and triples, when you consider some of the triples of A, B, A times B, so you have a finite group, and consider all those triples, A, B, A times B, and now take a subset of it. And the question is that, so for this special triple set, is it true that it's little n squared? And yes, for groups I can prove it. For groups, one can use a theorem, which I'm going to write in a minute, to prove the statement. What I'm saying is that whenever you can come up with a nice structure here, then there are tools to deal with the problem. In general, even this simple-looking problem is out of reach. But maybe there are some other conditions. This having a group and considering the triples, this is a very, very strong condition. I expect that something weaker is enough. Actually, for groups, I can prove the the general conjecture, but still, you are using a very, very strong structure. Can you find a weaker structure which is still enough? Now, just as a final note on this problem is that you can extend any linear, so again, and you can assume that your system is like this, that the intersection of any two edges is just 1 point or 0. They are disjoint. You can always extend it to a slightly larger one, but not more than twice as large, which gives you a kind of maximum system, a Steiner triple system, it's called. Or if you wish, you can encode it in a Latin square when you have the elements as a Latin square, and the third element, for every pair, you can write here the third element. And it's not much larger. So you can actually ask, but this is not, well, if you want, you can write a quasi-group here, but in my proof, I really used associativity, so I don't know what to do with that. But as a structure, as a weak structure, you can find something. It's enough to prove the theorem for triple systems coming from Latin squares, that if you have a positive fraction, if you take a positive fraction of a Latin square or a quasi-group, a positive fraction of such triples, then there will be a 7-4 configuration, 7 elements with 4 edges on it. For groups, I can even draw it. There is another interesting question which goes, so I proved it for finite groups, but it's expected that you can prove similar theorems for infinite groups. But in my proof, I really use the fact that every finite group has a large abelian subgroup, which is not true for infinite groups, clearly. But there are maybe other tools. So what I proved, which implied, so A, B, C, D, those are elements from the group. And so it says that I take some subsets, some of the triples, A, B, A times B. So I proved that no matter how you do that, you will find, oh, OK. You will find this. So this is AC, which is also BD, and this is AD, and this is BC. So this kind of substructure. So no matter how you choose a dense subset of such triples from a group, then you will find this thing. And I think that it's true in more general. So there are many. First of all, you can relax the group structure a little. And let's see the theorem which helps you to prove such statements. At least I know this tool only. And now I will check. It should be the first one, maybe not. As I promised, now something about hypergraph regularity. To really see the full power and everything, as I said, you have to juggle with epsilons and deltas, but not in this form. So this is a special case first, what I'm going to write. So this is a, what would be the best way to say it? Whatever. So it's a corollary of the hypergraph removal lemma. It's not even, I didn't even write that hypergraph regularity, it's removal lemma. So let's see the statement, and let's try so let's see the general form. So here is a notation, HNR. This is an R uniform hypergraph on n vertices. That means nothing else than sum of the R element sets, subsets of an n element set. So you consider, those are the edges. Like for graphs, you consider sum of the pairs of the elements. This is a more general case. Now you consider the R tuples. And one more thing, that the click, so that every edge has now R points, R vertices. A click, what do I write? Is a set of R plus 1 points where every R tuple, so there are R plus 1 R tuples, is an edge. So this is like a complete graph, and I will call it K R plus 1 R. So it's a complete graph on R plus 1 vertices. It means that you have R plus 1 points, and all R subsets are edges. You selected all of them. So this is a click. And the statement is that if in H n R, so this is a hypergraph on n vertices where the edges are R elements. So the maximum number of edges would be n choose R if you select all the R element. So subsets. If in H n R every edge is the edge of exactly one click, then the graph is exactly 1. I said 1. We will see an example in a minute. It's 1. 1. Then the graph is sparse. I will explain in a minute. So let's see for triangles. Let's see just for graphs. The statement is actually the Ruzha-Semeridi, but something like that. So let's see. You begin to draw a graph, and every edge is an edge of, in this case, 1 click, and only 1. This would be the click, yes? It's 3, and every tuple is there. Only 1. So this is not allowed. Another 1. So you draw it, and for example, like this. Yes, so every edge, I still have to work on it. Yeah, beautiful. So every edge is the edge of exactly 1 click. Here it says that every edge is the edge of exactly 1 triangle. Not 2, not 3, and not 0 in particular. Then the graph is sparse. In this case, it means that, well, if you begin to draw it, then you would expect that this is very sparse. But unfortunately, you can't say anything more than the number of edges is little n squared. And in this case, sparse means that the number of edges is little, what did we have, n to the r. Sorry? There are n vertices. The triangles, the number of edges. So it's, the graph is sparse. The number of edges is at most, well, it's little n squared. So it's sparse. And you can't say, unfortunately, I mean, I don't know what is fortunate or unfortunate. You can't expect to improve here the exponent. And this is the general version, you see. So this is a form very easy to remember. You have this very strange hypergraph that every edge is in exactly 1 click. Then it's sparse.
And if it's at most 1 click?
Exactly 1. one click.
So you don't have the statement
if it's more?
No, if it's in its most one click.
No, then you can have a bipartite or r-partite. So for example, there, if you see a complete bipartite graph that has many edges and no triangles and still no statement. But there is another direction here. Actually, it's true in more general if the number of, there are many variants of it, but I don't want to confuse you. This is one version. And just to show that, so this one already proves the multidimensional summarity theorem. So this one, this innocent-looking statement, what you see here, is enough to prove that if you take a dense subset of, say, the integer grid, n by n, then it will contain a square. Say that would be the simplest case. But actually, it will contain an arbitrarily large subgrid. Summarity theorem says that if you take a subset of the integers, a dense subset, then there will be arbitrarily long arithmetic progression. And this says that, well, the same true in a more general form in higher dimension. And let me just illustrate it, because for the higher dimensional things, that's slightly more involved. And I'm running out of time, almost.
You have like 10 minutes.
Yeah. So let's just show this one. It's something when Gowers proved his nice Fourier analytic method for summarity theorem, then at the end he asked this question, and I found a relatively simple answer using exactly this. So the statement we are going to prove now in 2 lines is the following, that if you have this integer grid and you have a subset S which is dense, say the cardinality is at least c times n squared, then if n is larger or equal than some threshold, which depends on c only, then there will be a corner. There will be 3 elements with coordinates x, y in S. X plus dy and x, y plus d. So this is already a more general question than finding 3-term arithmetic progressions in dense sets of integers. If you want to see that, just consider this line and the projection here. If you have a dense set here, above every point, you can take all the points there. So if you can find such a triangle, then that will, of course, give you a 3-term arithmetic progression here. But let's just stay with the statement itself, that there is a corner. How to prove it? Well, let's define a graph. One vertex set will be all the vertical lines, or the vertical lines which have at least one intersection with this. The other one will be the horizontal lines and the slope negative 1 lines. Those are the vertices now. And 2 are connected to vertices by an edge if they intersect in an element of S. So S is a subset. There are points. For every point, I defined actually 3 edges, right? The 3 pairs which intersect there. Now, every point will give you a triangle in this 3-partite graph, yes? For every edge, for every point, in S, we consider, so this is a point, there are 3 lines going through this point, which gives you a triangle, right? So the number of points is the number of triangles there. Maybe there are more triangles, but that would prove the theorem. Why? So if those are the so-called trivial triangles, which come from 3 lines going through 1 point. But if there is another triangle, that means exactly this. Right? So, but the statement says, this one here says that if every edge is the edge of exactly one triangle, which would be the case if there are only those degenerate triangles in this picture, so then it's sparse. So if the number of triangles is, there's another way to say that, if the number of edge disjoint triangles is c times n squared, then the total number of triangles is c prime times n cubed. So I gave you this, and I didn't talk about how to find groups in geometric problems, which is just a fantastic and very interesting area, but it's bad time management from my side. So let me just stop here, and thank you very much for your attention.